Okay, so in this video, what we want to do is talk about a little bit more on the terminated T-line. What happens if we have a complex load, right? What if there's an RLC load, okay? So that means that the load impedance is equal to R plus J omega L plus, or I'll say minus rather, J divided by omega C, right? So this shows us that we have a complex load, right? And depending on, is it, purely resistive, is it purely inductive, is it purely capacitive, or a mix of both, it behaves in a different way. So let's just take at least one case. What if it's terminated by a purely inductive load? So that means R is equal to 0, and that means that we have no capacitive component either, right? So in order to do that, we say that ZL then would just be equal to J omega L, or you could call that J times XL, which is commonly used for inductive reactance, right? So in doing so, we then say, okay, what does, well, let me jump back here a second. Instead of looking at the input impedance, what if we instead look at the reflection coefficient, okay? And the reflection coefficient, you remember, is equal to ZL minus Z naught and ZL plus Z naught, okay? And what I'm going to do is I'm going to say, okay, well, let's consider lossless line. So lossless line means it's purely real, right? It's real part. So I'll just call it R naught. That's the characteristic impedance. And ZL is JXL, okay? So replacing those, look what I get here. I get JXL minus R naught, and then I get JXL plus R naught, okay? So if you look at this, we'd say, okay, let's think about what the magnitude of the reflection coefficient is. Well, here's the reflection coefficient. Taking the magnitude of a complex number, I take XL squared plus minus R naught squared, square root, and then I have a complex number on the bottom, so I'm going to take XL squared plus R naught squared, okay? In either case, I get the square root of XL squared plus R naught squared, so the magnitude is 1. And when the reflection coefficient is at the load is equal to 1, that means all of the wave is reflected, right? So we saw this with the short circuit case. We saw this with the open circuit case. Now, if we have a lossless line terminated by a purely inductive load, we also see that all of the line is reflected, or all of the wave is reflected, okay? But we should notice here that we are going to get some phase shift, right? So what is the angle of the reflection coefficient? Well, remember, we're going to get the inverse tangent of the imaginary part, so XL, divided by the real part, so negative RL, and then we subtract, because remember, for when we're dividing complex numbers to get the line, we subtract. So we get here tan inverse of XL over R naught. And what you should note here is that inverse tangent is an odd function, so I can pull that negative sign out. So then the phase angle is negative 2 times tan inverse XL over R naught, right? So you can see the degree at which the phases change is going to depend on what is the value of XL and what is the value of R naught and what is the ratio to one another, okay? All right, so let's talk about our last and final topic here, and this will finish the video lecture section of this lecture. So now I want to talk about the complete circuit, right? So I put everything together. So now I have some input source, right? This is input VSS, means there's a source voltage, and it has its own internal, it has its own internal impedance there. We have a whole circuit which can be represented by an input impedance, right? So I can look at this and I can say, this kind of looks like this circuit right here, right? And we can use some basic circuit analysis to do this, right? So what I'm going to do is I'm going to say, okay, look, the input voltage, right? Seen at the input impedance, we can just use a voltage divider. I'm going to take the source voltage, I'm going to multiply it by the input impedance divided by the sum of the source and input impedance. Now this right here would give you, if you know your source voltage, you can calculate, well, your source voltage and you know your impedances, you can calculate what the input voltage is, okay? But is there a way that we can use that to find out the initial voltage of the traveling wave? And we can, okay? We should note that if we jump back here, what is this input voltage? Well, that's the voltage seen right here. So that's Vs of Z is equal to negative L, right? That's the voltage seen at negative L right there. That's the input voltage. So I'm going to say that's Vs of Z is equal to negative L, okay? And what I'm going to do next is say, well, I can use for any Z, I can use my traveling wave equations, and I'll say that it's equal to V0 plus negative gamma Z plus V0 minus e to the positive gamma Z, right? And that's just using my traveling wave equations. Then I can use the definition of the reflection coefficient, which is said is the ratio of V0 minus divided by V0 plus, right? And whenever I do that, I can solve this for V0 minus, right? So solving this for V0 minus, I would say V0 minus is equal to the reflection coefficient times V0 plus. And what I'm going to do is I'm going to replace that there, okay? And when I do that, I get Vz is equal to V0 plus e to the negative gamma Z, right? And then I'm going to replace that V0 minus with plus gamma L V0 plus e to the plus gamma Z, right? And the reason I'm doing that is because then I can factor that out, and I have V0 plus is equal to is equal to e to the negative gamma Z plus the reflection coefficient e to the positive gamma Z, right? And this will tell me what is my voltage at any single point along the line. You put in any Z and it'll tell you what my actual voltage is. But we don't know what this term is yet, right? So we probably know what the source voltage is, but we don't know what that term is. So let's solve for that. How can we solve for that? Well, we can solve for that using this right here, right? Because we know that the input voltage is equal to Vs when Z is evaluated at negative L, right? That's what the input voltage is, right? So what I'm going to do is I'm going to say Vin, okay, is equal to Vs evaluated at Z is equal to negative L. Well, I have that equation for Vs of Z for any distance. So I'm going to put negative L in there, okay? So Vs of negative L, okay? And I'm going to use this equation right here, and I'm going to get V0 plus, right? Now look, e to the negative gamma, negative L is going to give me positive gamma times L, and then plus the reflection coefficient e to the negative gamma times L. All right? Now we know the input voltage. We can calculate it using the source voltage. And we know the reflection coefficient, and we know the length of the line. That's L, whatever the L is. So now we can actually use this all to solve for this guy right here, okay? And when we do that, we get V0 plus, well, actually, let me write this over here so I can highlight it because this is an important equation. Sorry about that. We get that V0 plus is equal to the input voltage divided by e to the plus gamma L plus reflection coefficient e to the minus gamma L, right? Now, and you can use this at any time in your calculations, okay? So what is the important, oh, sorry about that. I wanted to highlight that. So what is the important thing here? So if we know the source voltage and we know our impedances, which we normally are going to be able to do unless we're designing something, we can then calculate the input voltage using those quantities. Using the input voltage, the length of the line, the reflection coefficient, and the propagation constant, we can then calculate V0 plus. Then we have the input voltage, we have V0 plus. We can use that to calculate the voltage at any point along a line. Okay, so this basically puts it all together and gives us all the tools to do whatever we want with this. Okay, so in the next lecture, we're going to do in-class Smith chart design. Okay, so we're going to have to watch those lectures in advance, and we will work on them in class. Okay, thank you. I hope you enjoyed this video.